Okay, recording. Here we go. I've had this project that I wanted to work on for quite a while, and I figured I'd record it because I think there's a fair number of useful things that can be learned. I want to show my process, um, explain what I'm doing, and it's pretty fun visualizations too. So it should lend itself to this. So I'm going to make a series of videos. This will be the first one. The basic idea is to use cellular automaton modeling to explore green bridges. If you haven't heard of a green bridge, the idea is it's basically just a bridge or potentially a tunnel designed entirely for the benefit of wildlife. I guess it's useful, nice for humans too, but the idea is that road networks, because of the way things work in two dimensions, kind of really reduce the connectivity of green spaces. And that is a big problem for the wildlife because they're either going to be too scared to cross the road or they will, but they'll get hit by cars. Um, and so, one proposal for remedying that is adding green bridges or green tunnels so that they have a migration pathway from one big green space on one side of the highway to the other. Um, so, I don't see a lot of these around. I think they're nice for humans too, because it can be very nice to be able to just walk around without having to be interrupted by thinking about crossing the road. And so the research question, which I've sort of posed as uh, how can we save, how much does it cost to save deer? But a more accurate way to put it would be how do we figure out where are the best places to put green bridges? Um, One way to answer that would just be, look for huge green areas that are separated by a road. That's sort of an obvious answer, and you might be able to use maps data and look at that. But to make that a little bit more convincing, the idea is maybe if we have a model behind trying to understand the movement of wildlife, then we might be able to really start to make arguments about if you put this green bridge in this location, it's going to really do a lot of benefit for the wildlife. The example wildlife we're going to use are deer. Um, and I think cellular automata are a good modeling framework for exploring this question because they are 2D models, and I think the dynamics of all these things can be represented in this framework. Um, haven't seen a cellular automaton before. It's just a 2D grid where each cell can have a couple different states, and there's update rules, usually just very local. So a cell will decide how to update its state just based on cells right next to it, or one step away, two steps away, three steps away. So we're going to try to start with something very simple. So let's just make a NumPy array. And we'll say grid is zeros. And maybe we'll just make it 50 by 50, for example. Events. And let's just have, for now, we're just going to have a very simple model. We have either field or deer. Um, in fact, let's be very simple. Let's see. So I'm going to say n equals 50. And we'll place one deer in the middle. And now we want to do our update function. So what I guess we'll do is write a function to update a cell given neighborhood of cells. Oh, whoops. Update cell. And we'll want to probably have a variable for time steps. We'll just do 10 of them for now. And we will step through that many times. And then at each step, we need to go over the whole grid. Let's arbitrarily decide that rows and columns, rows first, columns second. And let's do a pretty small neighborhood. So maybe what we'll do is we'll say we just want to take the grid and we want to go, the first pass would be like this. To pull out sort of a 3x3 square centered at row and column. But we're going to run into a problem with the boundary conditions. And I think one typical approach is to use a periodic boundary. So imagining that, yeah, you're in a 2D surface, but that 2D surface is on a sphere. But I don't really want to do that because I don't really want to think about the whole Earth. I kind of just want to think about like a city or a state, some county, some kind of region with edges. So what maybe we'll do is we will just go like that. And so we will consider the cells right at the very edge of the grid to be static. And now we can always just take the neighborhood with this slice. And in fact, let's actually save that to a variable called neighborhood. Oops. I think I just tried to run the cell by mistake. And then we will just update the cell by passing in the neighborhood. Well, yeah, so I guess what we'll do is save the output of that. We'll imagine that function is going to tell us what the new state of that cell should be. And let's actually do this a little differently. Let's change the shape such that add a dimension of size time steps. And maybe, no, I want to do that. Just kind of looks pleasing to me, makes me happy. Oops. I think we're going to want to do that. Okay. Cool. Good. And then, right, so then we get our new state, and we're just going to say grid. Okay, this is something that always comes up. So we actually, if we're going to update t times, then we need our grid to be, I'm just going to call it grids, the grid at each time step. And maybe let's we'll do it like this. Call it world. A bit more descriptive. Almost everything, any 2D matrix is a grid. Might as well call it something more specific. Okay, good. So, right. We're going to want to say worlds at row, column, and then, oops, actually, let's kind of keep going with this sort of mathematical type notation. And I'm going to check later when we display this that x and y are actually mapping up to, x the horizontal dimension, y the vertical dimension, just so that we don't run into really confusing problems later on. It's just one of those things you learn about if you do a lot of programming to watch out for. And then we're going to want to do t plus 1, I guess. So when t is 0, we're going to be setting the world state at the second. We're going to be setting the second world. Okay, and that we just want to set to the new state. Yeah, maybe a little verbose, but that's totally fine. Zen Python tells us to be explicit. So now in this function, we're just going to think about the neighborhood. And basically right now, let's pick out the active cell here. So we'll say middle of the neighborhood is the active cell. And then if the active cell is a dir, that's the only time we're going to actually do anything. And the idea that we're going for in this cell, or this code cell, a little bit of duplicate notation, is the dir is just going to move random orthogonal direction. We'll just say the dir does that at every time step. We don't want to wait around. Dir's not gonna sit there grazing. So what I like to do up here where we have our sort of constants, let's add some new ones. We're gonna have a list of directions, and these are just gonna be some basic tuples. And the nice thing, you can use tuples to index straight into NumPy arrays. So that's just some more nice notation we can use. So, oops. And I think we're going to want, I prefer just using the Python standard library random. So we'll do random for choice. Okay. And then, so if we're going to try to do anything at all, then we will do a random choice of directions. And we will say that our target cell is Okay. I think I'm gonna change up how I'm thinking about this a little bit, and we're gonna do it this way. We're gonna say, instead of the active cell referring to actual state, it's gonna refer to an index instead. We'll call it 1, 1 for the center. And then we just want to say if the neighborhood at the active cell is a dir, then our target cell is going to be the active cell plus the dir. And I think that's not going to work. Again, I'm having a notational issue. I'm saying dir uh, for deer, the animal, and dir for short for direction. I don't think you can directly add tuples like this. But what we can do is, let's see, I think what you can do is A plus B for A comma B and zip, sort of a, that's terrible, isn't it? Maybe what we'll do is just make a quick function to hold this code, because I'm just thinking ahead and I'm wondering if we're going to have to do this a bunch of times. I'm not going to want to see that a bunch of times. So what we'll do, oops, oh gosh. Maybe we'll say, okay, that feels like I should test that just to see if that's actually going to work. Let's just remove any syntax problems, and we're going to print, say, 1, 2, oops, nope. Add tuples. Let's do some tuple literals. So we'll say, can you add up these guys? Let's see here. Truth value of array. Oh. Truth value of an array with more than one element is ambiguous. Wouldn't have thought neighborhood at active cell would be an array with more than one element. That's odd. Oh, it's trying to run all this code. Well, okay, I guess we're just gonna go ahead and debug this right now. So let's just see what the neighborhood looks like for starters. Okay, that's not quite what I wanted. Oh, I think I certainly see why. It is because, let's make this a little more readable. Yeah, so this is where we just want to use T. Okay. Okay. Init argument must be a string. Oh, I see. We didn't return anything. So we're just trying to return. I don't know. I don't care. Turn deer. Boom. Well, we're doing a bunch of printing that we don't really want to be doing. What's going on here? It's just taking forever to. I thought I reran it without the print statement, didn't I? Okay, none. Oh, add tuples doesn't return anything. Problems with my return statements. Generator object. That's not good. Okay. Well, oh, why did I zip T1 plus T2? That is not what I wanted to do. No, didn't work still. Let me make sure I know what's going on. What does this do? Zip object. Okay, okay. I just want to check. Oh, apparently I just need to do that. Okay, cool. So that now should do what I want. And oh, yeah, so the target cell is going to be just gonna add up the active cell in the direction. Great. And then, okay, so the problem I'm thinking about right now is the the deer will eventually, theoretically, wander into the very edge of the world, and then it won't actually get updated in the next step. So actually, I think what I'm going to go ahead and do, since I know I'm going in this direction anyway, is we're going to put in a road state right away. And what we will do is, I'm trying to think about the best way to initialize roads around the edges. Um, yeah, I guess we can just say roads at, um, so at 0 everywhere, time step 0 equal road, and worlds at, yeah, n minus 1, or I can just say -1 everywhere, time step 0 is road, and just sort of symmetrically like this. Oops. Okay. And so then now we just need to add another check. So if I hate having to type neighborhood so many times, but it's not too bad. If the neighborhood, the target cell let's just say if it equals a field, then, oh, okay, another issue, which is that we don't just want to update the active cell. We kind of need to change the whole neighborhood. So maybe instead of doing this, we will just forget about putting this in a function and we'll just put all this code directly here. Forget about calculating neighborhood even. Let's do it differently. Okay, so there. Right, so then, yeah, the active cell, we will just say is XY. And now I don't have to type neighborhood. Great advantage doing this. I can just say worlds. The thing is, yeah, I don't like having to put T everywhere, but it's not too bad. We'll say worlds, active cell T, dear. Pick a random direction, add the tuples. Okay. If worlds at the target cell time T is a field, then we will actually update the next one. The next time step, the deer will go over there, and the active cell, the next time step, will be vacated back to being a field. Great. Okay, that ought to work. So now we want to actually visualize what's going on. And so for that, we are going to want a couple tools. So Matplotlib, obviously the go-to. So let's get, yeah, PLT imported. And we're going to do an animation because you can sort of re-show the plot at every step, every time step. But this is the more appropriate way to do it. There's this tool. Let's use it. And so now, let's see. Let's put a couple comments in here. Initialize, simulate. Oops, do that. Whoops. Okay. Display. Visualize. Okay. So now, yeah, we're gonna want color map. That's step one. So our color map will be some colors. Oh, a listed color map. And we're going to just use some built-in colors. So in the same order as the 0, 1, 2 of the field deer road, we will say green, tan for a deer, and then definitely gray for road, which will be our boundary for now. Okay, and then we need to make a figure and an axis. Okay, and then we need to set up this image with the initial state. So the first time step, we'll give it the color map that it needs, and then animated equals true. Okay. And then to do an animation, you need to define an update function, which takes in an integer for the frame of the animation, and then it changes the image depending on that frame. So in this case, boom, or no, obviously that. Okay. And then we actually create our animation. Now we're going to use that import the function animation, update function, and frame equal our big T plus 1. Okay, and then I think you have to do something like this. It's not quite that, though, is it? This is just because I'm working in a Jupyter notebook. Hold on. Yeah, let's see. Now you have to. Ah, I see. Right. There. This is what I think you have to do. And then can you, I know you have to import. Oh, okay, hold on. So from ipython.display import HTML. That's what it says to do. Let's see. The truth value, here we go again with this. Okay. Guessing it's because we're using this mixture of a tuple and so t, or t to index. So let's see what we're actually getting. Oops. Right. It does look like it's annoying. So maybe what we'll just do is to say world equals, whoops, that. Okay. And then we will not have to put in t every time we want to access the world in the loop, in the inner loop. Ugh, but then that's okay. Annoying, annoying, annoying. What is the best way to resolve this? We could do another variable. Let's see. I mean, no, that won't work either. Uh, NumPy. Tuples and integers to index. Let's see. Seems to think it's possible. Tuple of NumPy arrays. Is there a way to unpack the tuple? Can you just do a star? Wait a minute. No, I don't think you can do that. Ooh, wait. Unpack operator in subscript requires Python 3.11 or newer. What? Unpack operator in subscript. What version of Python is this using? Runtime. Python 3. Doesn't tell me the version specifically. I thought it did say this at some point. When it was first connecting. If I just restart. Yeah, it says Python 3. Oh wait, now it's not upset anymore? Interesting. Strange. Oh, it's back to being upset. Let's see, maybe it's not a real, maybe it's upset, but it'll run. That's possible. No, doesn't like that. Curious though, if I actually switch over, oh, and try this out, local Python. Let's see. Say grid, sample grid. And then we try to look at an index. So we want to do, okay, maybe I should match up what I'm trying to do in this example with the other one. I say boom, boom. Just try to print out that 0. And I say test. Okay. Oops. It does work. Yeah, I kind of want that feature, to be honest. So let's see here. Is it possible? Um, let's see. I want to know if Google Colab Python version. Colab updated to Python 3.10. Ah, damn. How to use Python 3.11 in Colab. Set new Python as default with update alternatives? Maybe this is possible. Let's see here. Okay, I'm going to pull this over so we can see what I'm doing. Do it this way. Okay. But you may want to need, yeah, okay, to update to a newer Python version for compatibility. Oh, interesting. Yeah, new language features, basically. What I would like. Where am I even supposed to be running this stuff is the question. Oh, I think I see it. So I have a terminal, right? Oh, I have to sign up for Colab Pro. Gain access to the runtime's terminal. But I have to pay for that, huh? Yeah. All right. Not worth it. Not worth it. Colab is not going to be the right environment anymore for this. So just grab everything and put it in my VS Code. Boom. Easy. Now we also don't need to do any of this. I believe we can just show these stars. This tuple unpacking should work. I wonder. This is fine. That's okay. So let's see here. Now I still have this file called test.py. That's okay. Test.py. Ooh, the deer is wandering around. You can't see it though. Hold on. Sorry. That needs to go away. This we will do that. And so boom, we have a random walk. Only runs for 10 time steps and resets like that. Boink. Boink. Okay. That's great. Something that's not going quite right though is that the road around the edge of the cell is only there on the first time step. So something's not quite right in our update function. And I think I know what it is. We're basically initializing everything at every time step to a field. So we just need to basically, let's be just a little bit more explicit with our updating. So else, if the world at the active cell and the current time step is, we'll be very explicit, is equal to a field, then the world at the active cell and the next time step is still a field. Great. And else if it is a road, we'll make roads sort of stable as well. Okay, great. Let's see if that fixes our animation just a bit. Oh, it did not. Oh, well, I know where that is too, actually. I think I want to leave the change that I made with explicit updates, but we're just gonna do this for all time steps right here instead. So that should fix it. Okay, great. Now we see the deer wandering around in this world where there's a road around the edge. I want to see if we can display a control bar. That's possible. Lib animation, or yeah, func animation, show controls. Can we do that? Um, I guess it's kind of annoying to do. It's okay. It's not super critical for right now. Let's do something. Let's do something simple. So what we're gonna do, let's shrink down the size of the world a lot. Let's add a lot more time steps. And I just want to make sure that the deer and the road interact correctly. They don't. You couldn't see it happen so fast, but the animation will get to its end and restart. The deer just vanished into the road, in fact. Which is interesting. I think I know why, though. Because we don't have an else here. And we should. So otherwise, again, let's be explicit. If our target cell is a road, then what we'll do is leave the active cell in the next time step as a deer so that the deer couldn't move. And now let's see what happens. Great. Okay, looks good. You can see deer's wandering around in this tiny little cage, fenced in pasture. Sometimes tries to move into the road and doesn't. So that behavior seems fine. Um, okay, so let's take a breath because we've gotten to the point where this is sort of a first checkpoint. Um, Because now we have this single random walker in its world moving around for a bunch of time steps. And so what that makes me want to do is to, okay, let's clean things up a bit. I'm gonna delete this other file and we will call this, yeah, this will be deer.py. Great. And then I think I'm just gonna see get init, okay. And then if I add deer.py, okay, and we'll say initial random walker deer. Okay, cool. Now we can go back to that if we screw everything up horrifically. But now let's think about what the next step would be. And I'm thinking that deer usually exist in herds. So we want to add more. Um, so let's do something stupid again. Um, so these cells are going to be putting a boundary. In fact, we will put some comments in. So instead of doing this, let's just we'll just put a little pack of deer. See what this does. Should do something right away. Boom. Huh. Yeah, okay. Oh man. Can I? Yeah, okay. Well, yeah. We'll have to wait for a sec. So there, you can see when the animation starts, yeah, the deer move into each other and a bunch of them sort of merge. No, strange way for deer to die, but it's happening. Um, so this is where we're running into a funny little issue because if if two deer try to move into the same cell, um, well, let's see. First of all, right, if it's a field, if it's a road, and otherwise it just becomes a field. So we need to be a little bit more careful. Otherwise, it could be the target cell at T could be a deer. Um, and in that case as well, we just want to not end up actually moving. Don't want to go to where the deer was. But I think there's still going to be an issue because maybe two deer at T both see they're next to each other and they see a field and they both move there. Um, so maybe a simple way to fix this is going to be to add a condition. So here's the case where we actually move. And what we're going to do is maybe just check that the target cell a step ahead uh, is not already set to a deer. I think if we do this, we're going to see, oh, okay, all the deer died. function. Here it is. Boom, instantly they all die. So why is that? Well, I think we're being a little too explicit now. Let's just say otherwise. So this is the one case where the deer can move. When the target cell is a field, um, and a deer isn't there. Another deer hasn't already decided to take over that field. And then otherwise, the just leave the. Oh, okay. We're running into some issues. The nice thing is um, the field's propagating into the future is going to overwrite deer. That's the issue. So, what is the best way to resolve this problem? Hmm. Typically, with cellular automaton models, you have each cell update itself independently. That's hard to do in this case, though, because we really need, if we're thinking about the deer moving to a nearby cell, it's not exactly a pure cellular automaton model because I don't really know how you would. Those cells have to update sort of in tandem with each other. Either the deer vacates the cell and moves to the other one, or it moves somewhere else. Um, you need to make sure the deer doesn't move in two directions at the same time. So you can't have a field become a deer if there's a deer adjacent to it. Um, well, maybe this will work actually. Maybe I'm overthinking this. Let's see what this does. Oh yeah, okay. So now we have our deer all starting their grid and they kind of start meandering. Um, I visually it's a little tricky to see if we get exact sort of conservation of deer. I'm gonna just try, oops, reducing down a bit to maybe 9 deer. Let's watch them. Still not the easiest to see. So maybe what we'll do, let's just for robustness, we'll go up to say 36 deer. And then what I want to do is just at the very end, just print. There should be a very easy way. There should be a one-line way to do this, a functional way to do this in NumPy. So worlds at the last time step dot flat Oops. Flat. Can I do like a on count? Okay. By count occurrences. By that unique. Let me do the array. Ah, I see. So I think probably the best way to do this is not flat. Let me simply say equal dir. Um, so now we get a new array of booleans. Oop. Yeah, I should be able to do that, I think. And just close the animation. The program is running 36. Great. Okay, so deer are being conserved. That's great. So now we sort of have a herd of deer. Let's just watch them for a while. Yeah, let's run this for say 200 steps. And bring this over. Let's just see what happens. So they're wandering around, behaving randomly. And I guess what I'm sort of expecting to see is that in the limit, they don't herd. They just, one's really gone far away, but they should just sort of distribute themselves all over the grid in the limit. Yeah, I started them in the corner, so they sort of stay in the corner. Um, but let's another checkpoint because now we have them functioning as a herd. Um, multiple deer. Cool. So what I want to do next is try to observe. We want to try to build in herding behavior for the deer so that they're slightly biased towards staying near each other. So maybe change how we initialize this. Make a little, make them start in the center. Boom. Okay. Oops. So this is where they've started in the center, and they're just going to kind of wander around. And yeah, you can see them ending up all over the place. So now we will be able to observe a difference if we actually build in some herding behavior. So let's go for that. So I think, right, that's going to come into play where we're picking our direction. We want to kind of bias that choice, essentially. I'm trying to think about how to do that. So what I'm imagining is maybe every deer has a look around uh, in the 5 by 5 grid. centered at its location, and is more likely to move if there's more deer in one of those directions. Um, let's see. So could we random choice weights? Is that possible? NumPy supports random choice probability distribution. Okay, great. So we just need to come up with a probability distribution, which, oh, and actually newer versions of Python let you do weights. Choices. Says, okay. Mm, yeah, okay. So we do just need, okay, great. So what's the best way to do this? We basically want to look in a couple directions. So if we look at world, say at a range of x's, and this is for looking up, that's what I'm going for. Well, I guess we won't necessarily know. And y to y plus 3. So y plus 0, y plus 1, y plus 2. Okay. At t. Right. And we're going to do the same little trick. How many deer? Take that slice of the world. Check if it's deer. Sum it. And so we need to, so that matches up with this one, that direction. Because we're checking every x in the 555 and y, where y increases. Yes. So we might want to make this code better in the future. But for now, let's just do something kind of stupid. And we'll say proms equal this. And boom. Okay. Okay. So matching this up with our directions. is that right? Y minus 2, y minus 1, and then y. Okay. And then similarly, uh, x minus 2, x minus 1, x, and all y's again, but then x plus 3. Should be good. X plus 1, x plus 2, y minus 2, minus 1, y, plus 1, y plus 2. Yeah. Okay. So these probabilities, it's not, we have to normalize this. I wonder if there's a way to, um, well, I just divide the whole thing np dot array. This, uh, that should normalize it. And then there's, so we need to do choices because this is the one that lets you pass in a distribution. And then I think it's a population and weights. Okay. Just say weights equal props. K-size list. So probably we need to do that. Let's see. Oh. Cannot. Ah, whatever. What if I just say this? Oh, okay. Let's watch. I think that this is quite different, qualitatively very different behavior from before. Because now they're not spreading out nearly so much as they were before. They're moving together, for sure. Sometimes one can wander away just by chance, obviously. Let's run it again. I want to make sure that I didn't screw up and accidentally introduce an asymmetry. So I want to see if I want to make sure that the herd on different runs will seem like it's not always going down or something. Maybe it is always going down. It's fun to watch now. It's gotten a little bit more split up this time, which is interesting. All right, let's do some things. I want to test a bunch of my assumptions. Let's make the world bigger, for one thing. Bigger world. A few more time steps. We'll have one herd of deer start in the middle, and we will have another herd that starts in the corner. Oh, what happened? Interesting. What happened here? Oh, wonder if it's because it's too close to the edge. That's probably what it is. Let's do something. Do a sort of stupid solution. Um, for yeah, -2 and 0 to 2, 0 to 2, -2. Oh, if I do, I got no, I'm doing this wrong. This is easier. Boom. Let's try that. Ah, bigger world, two herds, one starting in the upper left, one starting in the middle. Here's some escapees. But it does look like they are sort of sticking together. But we have some that get lost from the herd, or these, there's two forming their little couple. And they lose each other. Ooh, okay, the upper left herd is sort of split in two a bit. They do still scatter a bit over time. But they also tend to, I think they stay coalesced somewhat. Kind of just want a couple more deer. Let's just make them a big. Maybe not there. Do like add a bunch. Oh. Look at this. Oh, I added a bunch down here too by mistake. The corner. All right. Before we commit our changes on herding behavior, let's just test something. So if I change it to eliminate the herding behavior, like that, let's see if it looks different at all. Let's just make sure. It's probably a little harder to tell with a bunch of them. Oh yeah, I think that's already different. Yeah, look at that. You can totally see how much more they scatter. This is what it looks like without that. Let's watch again. Yeah, they spread out a bit. There seems to be like a stability condition on their dispersion, maybe, but this is totally different. Okay, neat. Great. So now we have herding behavior. Boom. Another checkpoint. So I think that's where I'm going to call it for this stream. Next time, though, we're going to actually switch to a whole new grid, and we are going to we're going to add apples, and we want to make sure that if the apples have no deer to eat them, that they kind of grow according to their rules, make that work independently, and then we'll put them together and calibrate the parameters so that uh, the deer can eat the apples.